In section 2.4, we're looking at rational exponents and nth roots. We're going to apply some properties to exponents, simplify exponents involving power to a power. We're going to expand the power of a product, and we're going to determine the nth root of numbers and write radicals as rational exponents. So all of these are various properties of exponents from this section. To get us started, we are making some decorations that look like dice, and we want the small die to have sides x by x by x, and the large die to have x squared, so whenever x is x squared units on all sides. So if our small dice has an edge of 2, then its volume, which is x times x times x, 2 cubed, would be 8. And if our large dice, again, if our small dice has an edge of 2, our large dice would have 2 squared or 4 as its side, and 4 cubed is 64. Also note that 2 to the 6th power is 64. So for confirmation, we're going to try this again. If our small dice has an edge of 3, then its volume is 3 to the 3rd, which is 27. And our large dice is going to be 3 squared, and 3 squared is 9, and 9 cubed is, let's move this up here, 9 cubed is 729. And then let's check what 3 to the 6th is. Oops, that was supposed to be on its own little line there. There we go. 3 to the 6th is 729. So through observation, we're looking at a pattern here. Again, one more before we talk about the pattern. 4 to the 3rd is 64. And then if my dice is 4 squared to the 3rd, 4 squared is 16. And 16 to the 3rd is 4096. And so I want to compare that with 4 to the 6th, which is the same. So what we're trying to show through this is that when you have the small base 2, 4, or 2, 3, or 4 squared and then raised to the 3rd power, you get the same thing as you do by raising that small base to the 6th power. So we're showing that x squared to the 3rd simplifies as x to the 6th. We also want to compare the graphs of these. So we've compared numerically that we're getting the same thing. We're going to compare graphically that we're getting the same thing. Just an illustration of this property. So if I graph y equals x squared to the 3rd, and I graph y equals x to the 6th, I can make one of these dotted and should observe that the graph of the two functions are identical. The dotted graph falls right on the solid graph line. I have the same graph. So the graphs are identical. What do the results demonstrate with the relationship? Well, it should be demonstrating that x squared to the 3rd is equal to x to the 6th, and that gets us to the property down here at the bottom, that if you have a power to a power, a to the n to the mth, or vice versa, a to the m to the nth, doesn't matter what order your powers are, you're going to multiply the two powers, a to the m times n. So x squared to the 3rd is the same as 2 times 3x to the 6th. All right, so we get to use this property a few times on the next page. There's an example at the top, and we're going to use the property for number 2. T to the 3rd to the 5th, that's going to be t to the 15th. I've got t to the 3rd, t to the 3rd, t to the 3rd, t to the 3rd, t to the 3rd 5 times. Altogether, that would add up to t to the 15th. If you were to add up the 3 5 times, or just multiply, 3 times 5 is 15. Same thing over here. Y squared to the 4th is y to the 2 times 4 is 8. 3 squared to the 4th, that's 3 to the 8th. 2 times a to the 5th to the 3rd. This 2 is not part of the exponential expression, so it's just a coefficient. It's not being repeated. So I'll have 2a to the 15th. Then for the next part, this x is not being repeated either, just like that 2 was not. So I'll have x times x to the 2 times 3 is 6. But that, since those are both x's, that can be simplified. I got 1x and 6 more, x to the 7th. This uses the multiplication property of exponents. All right, continuing on, we've got our -3 here, t to the 8th. T to the 8th seems pretty popular in this set. And we've got, in this one, this is not power to a power. I don't have any exponents on exponents. This one's just an example of multiplication property. So 5 times 3 is 15 for the coefficient. X to the 1st, x to the 4th, that's a total of x to the 5th. Y to the 2nd, y to the 5th is a total of y to the 7th. So this one's mixed up. It's really something that would have come from section 2.2. But again, mixing it in here makes us keep track of when we need to multiply the powers and when we need to add the powers. If we're multiplying the bases, we add the powers. If we are raising the base to a power, the two powers multiply. All right, now in number 3, there are a series of factors that we need to take care of. In this series, there is a group here in the middle that has a power on it. So we're going to use order of operations and deal with the exponent, the power to the power property first here. So I'm going to start by writing this as 2a to the 3rd times a to the 2 times 4 is 8, then times our 7a to the 5th. So we've taken care of all the exponent work. Now this is all multiplication, and we'll multiply the numbers together. 2 times 1 times 7, that's 14. And then a to the 3rd, a to the 5th, a to the 3rd, a to the 8th, and a to the 5th. We're going to add all of those up. So 3 and 8 is 11, and 5 more is a to the 16th. Okay. There were some examples at the bottom trying to lead us to this next property, that if you have a times b to the n, that the power on a product distributes, and you end up with a to the n times b to the n. And there's a couple of examples of it here. We'll use this property for number 4. So 2x to the 4th to the 3rd. I'm going to apply that third power to the 2 and the x to the 4th. So I'll have 2 to the 3rd, x to the 4th to the 3rd. Those can both be simplified. 2 to the 3rd is 8, x to the 4th to the 3rd power on a power. Those multiply to x to the 12th. All right, again, this power 2 is going to distribute to both of these. So the -3 is going to be squared, and the x to the 3rd is going to be squared. So -3 squared is 9, x to the 3rd squared is x to the 6th. We don't have to write down that first step all the time. We can just go ahead and do the multiplication once we become more comfortable with it. So we'll do that here. Go ahead and do our multiplication. A to the 3rd to the 2nd is going to be a to the 6th. B to the -3rd to the 2nd is going to be b to the -6th. And then I can use the property that says if I have a negative exponent, I can go ahead and move that into the denominator because my answer is supposed to be expressed with a positive exponent. All right. I'm just going to circle my answers before we go on to the next bit so that I don't get them mixed up with the work on the next few. All right, part D, there are 2 steps here. Again, I've got a power on a power. And actually inside those parentheses, since order of operations does say we should deal with parentheses first if there's anything to do inside of them, there is a multiplication property of exponents to do first. So we'll have several steps here. So I'm going to leave the x squared alone. I'm going to do the multiplication property on the inside. X to the 4th times x to the 5th, that's x to the 9th, then squared. So then we're going to multiply power times power there. X squared times x to the 18th. And then finally, another multiplication property of exponents. We're going to end up with x to the 20th. Okay, so lots of little steps to do there. And then in part E, power on a power property and power of a product property, both. We're going to do the multiplication on the exponent. We're going to distribute this exponent. So we've got our 3x, leaving that alone for now, -2 to the 4th power. So you can go ahead and do -2 to the 4th power. It's going to be positive because 4 negatives makes it positive, and 2 to the 4th power is 16. So positive 16. X to the 4 times 3 is 12. And then we have to finish the multiplication. Multiplication property of exponents, we're going to add the powers, but multiply the numbers like normal. 3 times 16 is 48. X and x to the 12th gives us x to the 13th. Okay, a couple more in number 5. Apply properties on each of these. The only difference in what I see in number 5 and what I saw in number 4 is that this is written as y equals, and those were just written as expressions where there was not a y variable. The y variable is not going to change anything in how I operate, but it is going to give me an opportunity to check. So this is going to be y equals 5 squared. That's 25. X to the 6th. And I'm going to go ahead and do this one here as well. I'm going to cube the negative. I'm going to cube the x to the 4th. 3 negatives makes a negative, so it's going to stay y equals negative, and then x to the 12th. With that y equals there, it gives us an opportunity to check. And any of these, we could have shoved a y equals in front of it and checked those as well. But with the opportunity here to check, let's show that y equals parentheses 5x to the 3rd squared looks the same as the graph of 25x to the 6th. So we can, again, just visually verify that our result matches up to the original. The dotted line from the result matches up with the original. And similar for the other one was negative x to the 4th to the 3rd, and I want to match this up with my answer, which was negative x to the 12th. And again, if I check that my dotted line and my solid are matching up, so again, graphically, I can confirm that the simplified result that I have here does match the original. So with the y equals there, it gives it the opportunity to check. Okay. Moving down to fractional exponents, we're talking about what a to the 1/2 power represents. And so a 1/2 power represents the square root. Okay, so they're giving us a demonstration of this below. And the reason for this is that the half power and the power 2 are opposites because the inverse of the square root is squaring something. So if we had what power is the same thing as the square root of a, and we squared both sides, it would give us what power times 2 is equal to power 1. And so if we solve for m, we get to the power is 1/2. So 1/2 power is the same thing as a square root. And while we're talking about those, moving on to the other side, if you have a cube root or a 4th root, the 1 over nth power is the same thing as the nth root. So little number in the index is the denominator of the power. Okay. So some examples here with square roots in number 6. Evaluate each of the following and check using your graphing calculator. So when I see 36 to the 1/2, what I'm thinking is that must be the square root of 36. So I know that I'm going to get 6. When I see negative 9 to the 1/2 power, the power is just in the 9, it's not in the negative. So I think that this is negative the square root of 9, and so that gives me negative 3. If I see the parentheses including the negative, then I think that this is the square root of negative 9, and I know that there is no real answer to that because I can't have two of the same real number multiply together and give a negative. Okay, and then 0 to the 1/2 power, I can do the square root of 0, and that is 0. Okay, so then we're going to talk about some cube roots for a little bit. We have a volume of an object here that is 64 cubes. Determine the length of one side of this cube. So L cubed is 64. So I need to figure out what number, when I cube it, gives me 64. Best way to do that is the cube root, opposite of the cube root. So L is the cube root of 64. I know that the cube root of 64 is 4, but if you don't know the cube root, you can compute it. I'm going to move my decimals graph back over here. There's a couple ways to do cube roots. One of the ways, by the way, if you don't know the square roots, there's a couple ways to do those as well. So I'm going to type in SQRT and the square root symbol pops up. So I can do the square root of, say, 36. Or I can use the tool palette and I can click on the square root symbol and do the square root that way. Okay, so I like to type just because it's a little faster for me than clicking on things in the tool palette. So if I wanted to do the cube root, I could do cube root. Think about taking out all the vowels and just abbreviating it. Cube root, CBRT. Cube root popped up for me there. CBRT of 64, and that gives me 4. Now, this symbol right here is only for square roots. There's no way to put an index into it. But if I wanted to use the button for the cube root instead of typing CBRT, I can go into functions and I can find the eventual, sometimes if my window's bigger, I have like tabbed options, but I can find the eventual cube root button. It would be in your last tab. My window is small right now, so I had to scroll down to get to it. But I have that nth root where I can enter 3 as the index, and then I can go back and enter 64 as the radicand. The inside is called the radicand, and get it evaluated. So uh, it's the last option in functions. It's in the bottom set there. Okay. Let me move my decimals graph out of the way, and I just explained verbally how I got the answer, so I did not write it in. Or actually, I wrote it in up here. I wrote that I was going to do the cube root, and that's how I got my answer. And we get number 8. We get to do some more cube roots. So you can check these out on decimals. The cube root of 1,000, that's 10, because 10 cubed gives you 1,000. The cube root of 0 is 0, because 0 times 0 times 0 is still 0. The cube root of negative 8. You can't do the square root of a negative, because 2 negatives would have made a positive. They don't make a negative. But you can do the cube root of a negative, because 3 negatives does make a negative, and it's just fine. So that's negative 2. And then the cube root of 100. That one I'm actually going to have to type into decimals because it's not a whole number. So if I want to do the cube root, I can just do the negative 8 one just to show you how it comes out as negative 2 for the last one. Then I can do the cube root of 100, and it comes out as about 4.64. They said to round to the nearest hundredth, so I'll round it to 2 places for the nearest hundredth. All right. Oh, they said nearest tenth. I didn't even read nearest tenth. I thought it was hundredth. So whatever. Take off the 4. 4.6, the nearest tenth. All right. Now on to number 9. Calculate each of the following. So these ones are fourth roots or fifth roots or fifth roots again or fourth roots again. All right. I will use the calculator to help just to show again how I can do this. When I get to the fourth root, I don't think that there is a way of typing it in like I do with the cube root. Although if you do, make yourself a cube root. I know that you can go back and change your index. So that's one way of typing it. I don't think I can type in fourth root though. But I can do the fourth root of 81 like this. And so it's 3. One of the easier ways to type this, instead of having to figure out how to enter the root, is to remember that a fractional power with that 4 as the denominator is the same thing as the fourth root. So I could have just entered 81 to the 1/4 power and not had to worry about inserting that radical symbol at all, just using 1/4 power. That's true of part B as well. 32 to the 1/5 power is 2. So I can get the answer from the exponent notation. Or if I really wanted to, I could figure out that I would need a radical with an index of 5 and a radicand of 32 to get me the same answer. We're going to do it again. This one's a fifth root. I'm still typing cube root just because I can type it faster than having to look for that button. and the radicand's negative 32, think about it, 5 negatives makes a negative, so this one should work. It's just when the radicand is even that you can't have a negative argument. So this one comes out as negative 2. And again, I do think that it is easier to type this in fractional exponent notation with a power of 1/5. And again, the answer matches. When I get to the next one, negative 225 to the 1/4. This one comes out as negative 3.873. I'll just run to 3 places there. And if I were to type this one into a radical, I would do the negative outside, and the index is 4, and the radicand is 225. And again, I should see that the same answer there is present. Okay, I'm going to keep decimals up here because I got to do another one where I try to compute the 4th root of negative 81, and it gives undefined. And why is it undefined? Because the index is even, and an even number of negatives would make a positive. So 2 negatives makes a positive, 4 negatives makes a positive. So there's no way that you would be able to have a negative number inside of a radicand where you have 4 of the same thing. 4 of the same thing would have been positive. 4 of the same thing cannot be negative. So this is going to be undefined. The reason that it worked for me in part D, where I had the even index, is because this negative is not part of the radicand. It's not inside. These are super exclusive little functions here. So if I write it this way, I will have to assume that just the 225 is supposed to be raised to the 1/4 power. And so if I had put it in parentheses, it would not have worked. So in parentheses, negative 225 to the 1/4 power is undefined, just like the negative 81 inside the 4th power. So without the parentheses, it means that the negative is outside, like here, outside of the radicand. It's not inside. All right. There, I'm going to move my decimals off now for a minute. There's a function down here at the bottom that I hopefully will use on the next page. Don't know what it's for yet. I don't know what each of those variables means yet, but here we go. I'm going to copy my function over. So L plus 1.25 square root of S minus 9.8 cube root of D and less than or equal to 16.296. Okay, so that's the function that we were given, where L is the length of a yacht in meters, S is the rated sail area in square meters, and D is the water displacement in cubic meters. So in order for a yacht to be eligible, that sum and difference has to be less than 16.296. So we're going to try to figure out if this yacht here is eligible. So the length of the yacht, L, is our 21.85. The sail area, S, is our 305.5. And the displacement, D, is the 21.85. So we need to compute 21.85 plus 1.25 times the square root of 305.5 minus 9.8 times the cube root of 21.85. And then we'll figure out if that's less than or our 16 value there or not. Okay. I'll have to move this around. Let me shrink my window just a teeny bit. There we go. So I should be able to see those numbers. 21.85 plus 1.25 times the square root of 305.5 x at the square root minus 9.8 times the cube root of 21.85. Okay, so what we get is 16.3. I was looking at the decimal place. So this equals 16.3. It is not less than or equal to 16.296. So the yacht is not eligible. Somebody's got too big of a yacht. All right. I gotta move decimals out of the way. Okay, so my answer was the 16.3 that I got did not satisfy the inequality. Somebody's got too big of a yacht. Sad problem. All right, so explain why the units are in meters. All right. Well, the units on the length of the yacht right here, this value, let me draw down. The units on this value are in meters. The units on the 305 are in square meters. So those are in square meters, but we're doing the square root of square meters. And then the units on the 21 are in cubic meters, but we're doing the cube root of cubic meters. And so the square root of square meters is meters. So this is meters. And the cube root of cubic meters is meters. So meters plus meters minus meters equals some number of meters. So that's why the units are in meters. We're adding up values that are actually in the same units. You can't add inches to square inches or meters to square meters. That's why it had to have their units coming out as regular meters before the addition happened. Otherwise, the value would not have had correct units. Okay, moving down to our rational exponent section down here, applying properties. So we talked about the denominator. If you have a base A raised to the P over Q power, the denominator is the index of the radical, and the numerator, if there is one, would be just still a power on the radicand. You can have this power written inside or outside, doesn't matter. It's just letting you know that you can evaluate the radical first or the power first, doesn't matter. So what does matter is the denominator pertains to the index. Any leftover numerator power parts just stays as a power. Okay, so some examples down here for us to compute. We have 25 to the 3/2 power. Wants us to compute these and verify in the calculator. So we can do these in our heads because we know the square root of 25. If you see 25 to the 3/2 power, this means the square root of 25 cubed. So square root of 25 is 5, and 5 cubed is 125. So it's possible by doing the square root first to make the number smaller that you're able to get the value. But again, if not, stick the whole thing in Desmos. 25 to the 3/2 power will give you 125. All right, this one. This is going to be negative the 4th root of 16 cubed. 4th root of 16 is 2, so this is negative 2 cubed, and that's going to give me negative 8. And again, sticking this whole thing in Desmos right here will give us the negative 8. So you don't have to do it by hand. It's just illustrating the fact that it's possible here. So I've got the cube root of negative 8 squared here. I'm going to put parentheses around the squared just because when I do the cube root of negative 8, it does give me a negative 2. And when I square that, I do get a positive 4. And again, if you stick this whole thing in decimals, it's going to give you positive 4. I don't know what the 5th root of 243 is. I'm going to guess it's 3, but this is one that I'll probably put in decimals to confirm. I need the 5th root. I'm not as good in my head at remembering 5th roots as I can do the squares and cube roots and so on. But I'm going to take the 5th root of 243. So let's do this one over here. Oh, I hate it when my screen is too small. Sorry about that. So let's go and find our 5th root. of 243. I thought it was 3. So that is 3. And 3 squared gives us 9. Now, again, as I wanted to show, there is no reason that you can't just type the 243 to the 2/5 power in the first place to get 9, which was my final answer. Perfectly fine just to do that. Okay. So down here, if I was going to do it in my head, I would think that the 5th root of 32 is 2, and then 2 to the 4th is 16. So the final answer in that one is 16. So if it was to the 4/5 power, I would do the 5th root of 32 to the 4th, then 2 to the 4th is 16. This one has no real answer or undefined, and that is because I have a even denominator on a negative argument, negative radicand. I'm not going to be able to do that one. So even if I type that one in decimals, it's going to say undefined or no real answer. All right. Okay, before I move decimals, I should have read my next question. This one is not going to come out evenly because I don't know what the cube root of 7 is. So we can evaluate this. 7 to the 2/3 gives us 3.659. Then it asks me to explain why this is reasonable. Okay. Well, because my denominator is 3, I will probably think about things that I know how to cube root. The smallest thing that I know how to cube root is 1, since 1 cubed is 1. The next largest thing that I know how to cube root is 8, because 2 cubed is 8. And if I took 1 to the 2/3 power, also noting to myself that 7 is between the outputs, 1 and 8 right there. So if I took 1 to the 2/3 power, that would be 1. That's less than or equal to this answer. And if I took 8 to the 2/3 power, the cube root of 8 is 2. 2 to the second is 4. So my answer for 7 to the 2/3, that 3.6, it's between 1 and 4, right? It's between 1 and 4, closer to 4 because 7 is closer to 8 than it's closer to 1. So I can check for reasonableness if I explore values around that 7 that I know the cube root of. I can think about reasonableness. Okay. All right, now we get to write these with fractional exponents. Okay, so the cube root is the same thing as x to the 1/3 power. The 5th root of x cubed, that's the same thing as, remember the 3 stays in the numerator, the index is in the denominator, that's x to the 3/5 power. This is going to be the quantity x plus 1 to the index is the denominator, so to the 1/4 power. This is going to be the quantity xy to the, there's no index shown, that must be a square root, so the index is 2, so the 1/2 power. Okay, so now we're going to apply the regular multiplication property of exponents, which says if you're multiplying your bases, add your powers. So if I'm going to add 1/2 plus 2/3, we're going to get common denominators. So this would be 3/6 plus 4/6, which is 7/6. So this is going to be x to the 7/6. You don't have to do your fraction work by hand, but we do need to add those fractions. I do need to know that those fractions are added. I can't type this one in, but I can type in that I need to take 1/2 plus 2/3, and that I will get the fraction 7/6. Then I can also check it by graphing y equals x to the 1/2 times x to the 2/3 and seeing that the graph I get is the same graph as the graph of x to the 7/6. And if I slide my graph over and make this dotted first, I could verify that the graphs do match, so my answer matches. Okay. So, we don't have to do the by hand common denominator business, but I do need to know that when I'm multiplying the bases, I'm going to add the powers, and I can add the powers and get the result. All right, and then over here, this is power on a power, so those two powers are going to multiply. So when I multiply those together, I need to multiply 3 times 3/4. This is going to give me x to the 9/4. You can double check that. Take 3 times 3/4. You should get x to the 9/4. And then over here, those two powers are going to subtract. So you can verify that when you subtract 3 minus 1/3, 3 needs a common denominator, so that would be 9/3 minus 1/3. It should give me 8/3. Again, you can verify that 3 minus 1/3 is 8/3. So my answer is going to be x to the 8/3. Okay, determine the domain for each of the following. We know that inside of a square root, because this index right here, it's 2, it's even, can't have a negative argument. So the domain for these is that x has to be greater or equal to 0. No negatives inside. But if it's a cube root where the index is odd, it's okay to plug in a negative or a positive. So the domain is going to be all real numbers or negative infinity to infinity. I did write this one in inequality notation. I could write it in interval notation. This would be bracket 0 comma infinity if you wanted to see it expressed in intervals, since I happen to write an interval over there. So x greater or equal to 0 or 0 to infinity, depending on if you want inequality or interval notation. All right, so we've got a new function, square root of x plus 2. Put some inputs into it. So in the first one, this is the square root of negative 2 plus 2. That's the square root of 0. That's 0. The next one, plug in 0, square root of 0 plus 2. That's the square root of 2. If you get that into a decimal, it's 1.414, etc. And then if you do the square root of 7 plus 2, that's the square root of 9. So that's 3. And then if we plug in the negative 6 plus 2, that's square root of negative 4. That's undefined. Undefined or no real solution for that one. So again, it's hard to sometimes see what my answers are when I have a lot going on. So I'm going to go back and circle those. All right, almost done. So I have 2 left here. This one's a cube root function. I'm going to plug some stuff into it. So first, the cube root of 5 minus 5, that's the cube root of 0. Cube root of 0 is 0. Then I'll have the cube root of 13 minus 5. That's the cube root of 8, and the cube root of 8 is 2. And the cube root of negative 3 minus 5, that's the cube root of negative 8, and that's negative 2. Again, I don't have to do these by hand. They're a little faster for me to do that way because I've had a lot of practice with cube roots and square roots. If they're not, that is not a big deal. What you will do to compute these, if you're looking at me doing them by hand and not wanting to do that, is you will write in your function f of x equals the square root of x plus 2, and you will evaluate f of negative 2. It's 0, like I said. You'll evaluate f of 0. It's 1.414, or square root of 2, like I said. You can do your f of 7 the same way. It's 3. And you can do your f of negative 6 the same way. It's undefined. It's not a real number. Same thing for g of x. G of x equals the cube root of x minus 5. We're going to plug in some values. We've got some cool looking functions showing up there too in their graphs. So we wanted to do g of 5. It's 0. We wanted to do g of 13. It's 2. And we wanted to do g of -3, it's -2. This is perfectly fine to have the technology help you evaluate these. So do so. Last question. Area of the base of a cube is related to the volume of a cube by the formula area equals volume to the 2/3. Determine the base area of a cube having the volume of 216. So the area would be equal to 216 to the 2/3 power. Let's just use Desmos to help us with that computation. 216 to the 2/3 power is 36. So it would be 36 square inches.